Thanks so much for coming and putting up with a few minutes of technical difficulties. Okay, so I'm here to give a lecture today on exploration in meta-reinforcement learning. And so this is just a little outline of the things I'm planning to talk about. So first, we're going to recap policy gradient and how we can use that to build some meta-reinforcement learning algorithms that Chelsea touched on last week. And then we're going to look at the problem of exploration a little bit more deeply. And finally, before the break, see an approach to encourage better exploration. Then we'll have a break. And afterwards, we'll come back and take a bit of a different view of meta-reinforcement learning, framing it as a POMDP. And then we'll look at how this framing allows us to design a different algorithm that crucially is off policy, so much more sample efficient, and uses a bit of a different way to explore. And at any point, please raise your hands, ask questions. Interactive is always better. Okay, so just to kind of motivate the whole problem statement, learning approaches have really excelled in producing agents that are specialists, right? They're good at one specific task. But in the real world, we'd like our agents to be generalists, skilled at a variety of behaviors, and able to exploit the structure in the world in order to learn new things faster. So here's a nice little toy example with some art. Surfing, skateboarding, and sledding all involve balancing your body on the board while it moves, right? So we'd like the agent to be able to extract this kind of shared knowledge between the tasks in order to learn a new similar task faster. So let's briefly go back to how meta-learning works in the supervised learning case, just to build up some common formalism. So in the supervised learning case, say image classification, we'd like to be able to recognize new classes from just a few labeled examples. And we'll do that by training across many such small classification tasks in our training set. So just to get some notation, we'll say that our training set is dtrain, and we're going to use some function f theta, which I'm not going to describe at all right now, and just say that f theta extracts some task-specific information that I'll call phi I. And then I want to use phi I to make predictions on the test set, right? And so then I compute the loss, and I sum over all of my training tasks. So my goal is to maximize performance across all the training tasks. Okay, so now let's add the RL formalism in side by side. So in RL, now instead of adapting to a new classification task, we want to adapt to a new MDP. So suppose we have some, again, going back to our set of MDPs that involve balancing yourself, right? So we want to be able to train across the set of MDPs in order to generalize to a new one. And so the notation will be largely the same. Again, we have our f theta extracting task information phi I, and we'll use phi I to try to maximize our expected return in the new MDP. So just to get some terms down now to be clear, I'm going to call this f theta entity the adaptation, or sometimes the inner loop. And we'll call this outer optimization the outer loop or the meta-training. And so as we look at these different algorithms, we'll keep coming back to what does meta-training look like and what does adaptation look like. And so meta-training will generally just simply be stochastic gradient descent on this objective. But we'll see a lot of different choices for how adaptation can work throughout these algorithms. Okay, so let's look a little deeper at the differences between these two frameworks that I've written down. So what's the difference in RL? Well, in supervised learning, notice that that new task that we're given, all the data is given to us, right? Someone gave us the training examples that were labeled. And so all our job was to figure out how to adapt quickly given that data. But now if we consider the RL setting, when I want to compute f theta of mi, where m is the MDP, I have to figure out how, like I'm not usually given the, say, transition function and reward function that explicitly define the MDP, right? I'm given experience. And I have to choose what experience I'm going to use to adapt. So we introduced this problem of exploration in addition to adaptation. So now your job is not only to adapt, but also to collect the data that will best allow you to adapt. Okay, so let's go back for a second to policy gradient so that we can build up a meta-RL algorithm. So in policy gradient, we're doing direct policy search with a policy pi that we're going to parameterize with theta. And so we'll simply run the reinforce algorithm, which I think Chelsea mentioned last week, where we'll sample data from our policy, and then we'll compute the policy gradient to update the parameters. And this is really just kind of a formalization of trial and error, right? You're trying to make good trajectories more probable and bad trajectories less probable. Okay, so how can we turn policy gradient into a meta-learning algorithm? Well, intuitively, what we want to do is collect and remember information as we go, right? As we collect experience, and we want that information to kind of inform the next action that we take. So this kind of starts sounding like a recurrent network, so let's just try plugging that in for the policy. So the idea is our policy is just going to be a recurrent network. We're going to train with policy gradient as usual, and we're going to train across a bunch of different meta-training tasks. Right? So I'll sample a task, in this case sledding, I'll roll out a bunch of experience from it and through my RNN, and through each time step that I accumulate, I'll be updating the hidden state of the RNN, right, which will inform my next action. And so as I train across all of these tasks, I'll be optimizing theta such that I get theta star. And what theta star will represent is like a learning algorithm for a new task, right, where the learning happens through the recurrent update of the hidden state. So to kind of keep track of all this in the upper right-hand corner, I'm just going to keep that RL formalism that we wrote down at the beginning. And so now our choice of f theta here is just an RNN, right? And we're still doing policy gradient on the outside loop. And so one note about this is that you may be wondering, like, how is this different from just using a recurrent policy in general? And one difference is that we want to persist the hidden state across episodes, right? Because we may want adaptation to extend across many episodes. Okay, so what are the pros of this method? It's pretty general and it's pretty expressive, right? RNNs are very powerful models. One con is that it's not consistent. And what I mean by consistent is that we don't really have a guarantee that the RNN learning algorithm will converge or what it will converge to, right? We're just hoping that by optimizing with the outer loop, it'll do something reasonable. Okay, let's think about a different approach. So what if we made the inner loop look just like the outer loop? So remember, the outer loop is policy gradient. What if we just do policy gradient on the inner loop too? And you guys have seen this already. This is MAML, right? Model agnostic meta-learning. And so the idea is we're trying to find some parameters theta such that when we take a few gradient steps on that theta, we'll get to a theta star that's optimal for a given MDP, right? So here we'd expect theta star 3 to be optimal for skateboarding and theta star 2 to be optimal for surfing. So again, in our little figure up on the right, now the outer optimization is PG and the inner one is also. So what's a pro of this? It's consistent because now the adaptation step is gradient descent, right? And we know what gradient descent converges to. It converges in nonlinear settings to local minima. And it's clear that in the limit of enough data, it would just reduce to reinforcement learning, so we know that we would eventually acquire the optimal behavior. So this is a nice property. One con is that it's not as expressive as the recurrent model. So question, can you think of an example MDP in which the recurrent method would be more expressive? So what happens if the rewards are 0, or if in general if the rewards are sparse? So if the rewards are sparse, then what does the policy gradient look like? Say you get one trajectory and you collect 0 rewards. What does the policy gradient update look like? It's 0. Like, you don't update at all. Which is kind of silly because you actually should have learned some information from getting no rewards, right? First of all, you learned about the dynamics of the new environment, which may have changed. And second of all, you learned that that's a really bad place to go because you didn't get any rewards. But this formulation is not really able to capture that, whereas the recurrent method we saw before would be able to. Okay, so let's look at how mammal-based algorithms learn to explore. So here's a computation graph of what's happening when you adapt with mammal. So you start with your policy pi theta, right, on the left. And then you collect some data, tau, some trajectories. And we use those trajectories to do an update, u, which is a step of policy gradient. And that gets us our adapted policy pi theta prime in the middle. Right? And now what are we going to do? We're going to, again, collect data with our adapted policy. That'll be tau prime. And we'll evaluate, right? We'll look at the rewards that we got for those trajectories. So the goal is to assign credit, like give credit for those rewards to both the adapted policy and the pre-adapted policy, right? Because the pre-adapted policy should get credit for doing whatever exploratory behavior led to good results later on. So that's exactly what happens. So if you write out the gradient, what you get is this kind of credit assignment where it takes the structure of the problem into account. So it takes that causal relationship between the tau prime and the theta parameters into account when we compute that gradient. And RL squared is similar, right? Except for now it's happening in the context of an RNN. So through backprop through time, the steps you took earlier in the trajectory are getting credit for the rewards received at the end of the trajectory. And if you want a few more details and the derivation for how this works out, it's kind of interesting. And you can find it in this paper, Rothfuss et al. 2018, and I'll also have the reference at the end of the slides. Okay, so we've just kind of hand-waved our way through with the idea that these algorithms are capable of learning to explore, and if we could optimize them perfectly, they would learn good exploration trajectories. So let's look at how they actually do in practice. So this on the left is the recurrent approach that we saw first, and the goal here is to adapt to new maze configurations. So it's been trained on a bunch of different looking mazes, and now we're asking it to adapt to this maze layout here. And so the goal is you always start in the blue square and you want to end up in the red square. And so what we're seeing on the left is first some exploration trajectories, and then on the right, the final trajectory that the recurrent policy produces. And so we see pretty nice coverage of the maze here, right? It goes way out, kind of explores one direction, and then goes back. So it's probably covering more than 50% of the maze. And then on the right, we have a different kind of example where we have gradient-based meta-learning in a kind of navigation setting. So what's happening here is the rewards are initially sparse around the initial position, and then you start getting some reward signal as you move further away. So it requires you to learn exploration trajectories that explore far enough away from the initial position. And in this case, it's working quite well, right? We have the blue trajectories as the exploration trajectories, and they're successfully going far enough away to get reward signal such that the yellow trajectories solve the task.
Yeah, I have a question.
Yeah.
Just make sure I'm understanding the recurrent method.
Mm-hmm.
You're learning a hidden state and an RNN that then just generalizes well in these different tasks.
Yep.
That's a general approach.
Yep. Yeah, so you just make the policy an RNN. You keep rolling out across episodes, and you train it across a whole set of tasks. Yeah.
The key part being that you keep that hidden state the entire time.
Yeah.
Okay, and then for policy gradient, if we're focusing on policy gradients here, would it be possible to swap in Q-learning for policy gradients in most of these cases?
It does not work well, or at all, in pretty much all of the research so far. It's definitely an active area of research. So in the second half of the talk, I'm going to talk about one approach that does work for off-policy RL, but certainly combining these approaches with off-policy RL is a very interesting and actively researched topic, but we haven't figured it out yet. Okay. But in other cases, of course, it doesn't work so well. So here's an example of, here's gradient-based meta-learning trying to explore in this sparse reward environment. And so I'm just showing two different environments here. In the first, the agent is the ant, and the second, it's this kind of cart thing. And on the right, I'm plotting, so the job of the agent is to navigate out to one of those little red circles kind of on the unit circle. And so to explore effectively, it needs to be able to reach that outer rim, right, so that it can get any kind of reward, so that it can figure out how to complete the task. And so then what's being plotted in these diagrams is the actual exploration trajectories that you get when you run mammal. And as you can see, they're not able to explore coherently enough in order to solve these tasks. So there's some more work needed here. Okay, so let's think about what the problem is. And I want to start by just giving some intuition for the problem here. Let's see if these work or not. Oh, yes. Okay, so here's a video of a child exploring, or what I would call exploring, right? And as you can see, her behavior is very kind of coherent. Like she picks a strategy and then she executes on that strategy for some amount of time before switching, right? And as a result, she's able to kind of explore in much more meaningful states, right? She's not waving her arm around out here away from the box. She's exploring in the states that are relevant for inserting that shaped peg into the box, right? And then by contrast, here's what exploration in RL usually looks like. So this is at hyperspeed. But as you can see, it's not exploring in the same kind of meaningful states, right? It's spending most of its time not interacting with the object and just kind of like doing random exploration in the joints. So what we'd really like is to develop a method that has this temporal coherency that we see on the left, right? Okay, so now getting a bit more technical, let's think about this problem a bit more. So we know that we want exploration to be stochastic, right? Because we need to collect a whole bunch of diverse data from different behaviors. And whereas optimal behavior is deterministic. So optimal behavior and exploration policies are quite different, right? And it can be hard to represent both of those in the same policy, especially when you have time invariant action distributions. And typical methods of adding noise to get that stochasticity are time invariant, right? So you might have a stochastic policy as on the left, but then there's no correlation between noise at each time step, right? Or you could noise the policy parameters, but again, kind of same problem. So we'd like a bit of a more explicit way of getting these temporally coherent trajectories. And it seems like we should be able to use our meta-training tasks to do this, right? We've got a whole set of tasks, and we should be able to learn some kind of strategy that would work well for other tasks of that nature. So let's build on top of the gradient-based meta-RL that we saw so far. And the idea here is we're going to augment the policy with a latent variable z that will inject the structured exploration into the policy. So we're going to do this by sampling a z and holding it, so I'm going to refer to that latent variable as z. So we're going to sample a z and hold it constant across the entire episode, right, which will give us our kind of input correlation. And then we'll enforce that that z gives us something relevant to the task through meta-training. And the way that we're going to do that is by adapting the z to give us optimal trajectories. So the way this is going to work is we're going to start with a prior on z, right? We'll sample a z from that prior and use that to collect exploration trajectories. Then we'll adapt the z via gradient descent, and we'll then enforce via meta-training that gives us optimal trajectories for that task. So in the RL diagram on the upper right again, our outer loop is still policy gradient, but our inner loop is now policy gradient on these z variables. Any questions about this? Yeah?
In this setting as well, are you using an RNN-based policy?
No, here I'm using the gradient-based approach. So all the policies will just be feed forward, and we'll do adaptation via gradient descent. Yeah. Okay, and of course the result we're hoping to get is if your job is to pick up one of these shapes here, rather than doing kind of random incoherent exploration, we'd expect the agent to systematically explore by picking up each different block. Okay, so this was a method that was published and called Mason, And so here we're going to look at some results from that paper. So here the task is to push one of these colored blocks across the table. And the agent is this kind of disembodied gripper here. And so we're going to compare what happens when you do mammal and when you do mason, which is that structured exploration we just talked about. So when you do mammal, we find that the exploration is kind of random and incoherent and doesn't succeed at pushing any of the blocks across, and so is not able to get a signal about which one is correct. Whereas if we train with this latent variable model, the exploration policy systematically pushes blocks across the table because it knows that the task distribution involves that, right? So it just needs to figure out which one. Okay, any more questions about this method? Yeah.
So this is like after some amount of, I guess, pre-training?
Yeah, so this is the meta-trained policy. Yep. Yep. Mm-hmm.
What is your definition of an episode?
Can you elaborate?
I was just wondering if like it was task specific or if it was just like because you said you're adding in the z latent variable for each episode, and then like I was wondering if that changed or updated across episodes.
I see. Right, so an episode only contains a single task.
Yeah.
You can't switch tasks in the middle of an episode. So if you were to think about the more realistic setting of kind of continual learning, then we would basically break it up into, we could potentially make episode and task be the same boundary just whenever the reward changes or the dynamics change. Right, so you have kind of choices here about how long you want to stick with the current latent variable, and that's kind of heuristic. Cool.
What was
Okay.
the reward here? Sorry.
The reward?
again for this problem?
I believe the reward is sparse until you get so far to the right. So you need
Right block.
Yeah, I'm not sure if you might get a reward when you move the wrong block too. I'm not sure, but I think it's only for the right one. Okay, so let's take a bit of stock of where we are. So what do we want from a meta-RL algorithm? And we're going to compare the three that we've looked at so far. So we have the recurrent one, the gradient one, or mammal, and the structured exploration one, or mason. So we talked about consistency. We said that the recurrent one's not consistent, but the gradient one and its derivative, of course, are. We talked about expressivity and why the gradient-based ones are not as expressive. We talked about structured exploration and how we can endow the policy with the capability for structured exploration. But finally, what about efficient and off-policy algorithms? So everything that we talked about so far has been based on policy gradient. And policy gradient is very sample inefficient, right? Partly because it's on policy. So it has to collect new data each time it wants to do an update. So we haven't looked at this question at all yet. But this question is pretty important, and we know from single task reinforcement learning that off-policy algorithms are 1 to 2 orders of magnitude more efficient in terms of samples, right? And they can achieve just as high performance. So this is something that we'd really like. And it also makes a huge difference for real-world applications. So if we're talking, for example, about wanting to run meta-RL on a robot, all the algorithms we just looked at would be kind of hopelessly sample inefficient. I calculated with kind of a control frequency of 20 hertz, and say you ran the robot continuously, and it would take about a month to train mammal on the robot for a reasonable task distribution. And so if we could bring these off-policy methods to bear, we would cut that down to maybe 10 hours, and we could run that. So this is a really important question that we're going to look at next. Okay, so why is off-policy meta-RL difficult? As a disclaimer, this is a very much unresolved question, and there's active research into trying to figure this out. And it's also very related to why off-policy RL is hard, too. So a lot of the reasons overlap. But one reason that I want to point out is that a key characteristic of meta-learning is that the conditions at meta-training and meta-test time should match, right? So what I mean by this is, let's go back to the image classification case. And let's say that your meta-training distribution consisted of classifying these dogs, these Dalmatians, German Shepherds, and Pugs. Now, when you go to learn a new class, you're going to have a much easier time learning to classify corgis, which are kind of in distribution, versus, say, motorcycles, which are not, right? And so we can make the same statement about RL. So when we have our meta-trained policy and we roll it out in our new task, that's going to be on policy, right? We're going to be collecting on policy data that we want to adapt from. But we just said we wanted to make use of off-policy data during meta-training. So now we're presented with this kind of distribution shift where we know that we have to be able to use on-policy data, but we don't want to have to use it exclusively during meta-training. So that's what let's take a short break now, and then after the break, we'll talk about how we're going to address this problem of off-policy RL. Okay, so we're going to switch gears just a bit and talk about kind of a different way to think about meta-reinforcement learning, and then we'll circle back to how this impacts our design of an off-policy algorithm. Okay, so POMDPs. A POMDP is just a partially observed MDP, right? So what does that mean? That means that we have some state which is unobserved to us, but we have access to observations, which are here noted as O, which give us kind of incomplete information about the state. And so an example of this might be that you have incomplete sensor data. There might be occlusions. Perhaps to do the task, you need an estimate of your velocity, but you only have an estimate of your position. Things like this are kind of usual examples of a POMDP. So it's a very, very general framework, and in general, very, very difficult to solve. So let's see how we can put our meta-RL problem into this POMDP framework. So if we write down meta-RL as a kind of graphical model, then what we have is essentially an MDP, right? But where the rewards and the dynamics functions are also dependent on this task variable. And in general, we don't observe the task variable, right? That's our job during adaptation to kind of, we could think of adaptation as figuring out what that task is, right? And so we can just redefine things a little bit and put this in the POMDP formalism. So let's just call that hidden state to be the concatenation between our true state and the task. And now we don't observe it anymore because we don't know the task. And we'll just redefine our observations to be the state and the rewards. So you could extend this a little bit more into a partially observed meta-RL problem, right, where there's also some other part of the state that you don't observe. Say you're doing meta-RL from images or something. But for now, let's assume that we do observe the state, and the only thing we don't observe is that task. Okay, so let's think about how we might go about trying to solve a POMDP. So a good strategy might be to maintain a belief distribution over what state we're in, right? So let's take this really toy grid world just for an example. So there's 3 states, and they're called S0, S1, and S2. And you're the circle agent, and you start in the far left. And in this MDP, the goal is to get to state 2, right? And you get no rewards until you get to state 2, and then you get a reward of 1. So when you first start out the episode, you don't know where you are, right? So you might assume a uniform prior over what you think your state is, assuming you have no other information. So that's what I'm illustrating there on the right with the blue boxes. Okay, so now let's say we take an action left. We hit the wall, we don't go anywhere, we're still in state 0, and we get a reward of 0. So now I know exactly where I am because I just hit the wall, right? So I could say with 100% certainty, I'm in the leftmost state. Okay, so how does this work for when we're thinking about the meta-RL POMDP? So now we're considering a whole set of MDPs, right? So let's take the same grid world, but let's define 3 MDPs on it. And I'm just going to change the reward function between MDPs. So for MDP 0, you get a reward of 1 if you're in the leftmost. For MDP 1, you get a reward if you're in the middle, so forth. So now, let's say you have observed where you are, but you don't know what the task is, right? That's your job in meta-RL. You want to figure out what the task is. So let's say, again, that you start out with no prior knowledge. You have a uniform belief that you could be in any of the tasks. And now let's say you take the same action. You go left. You hit the wall. You're still in state 0. You get 0 reward. Well, now you can update your belief, right? Because you know you're definitely not in MDP 0. Because if you were, you would have gotten a reward. So we could do this, and as we take more actions, we can update the belief more and more, so we have a better idea of what task we're in, right? And as we get a better idea, we can act more and more optimally. Okay, so now we have an idea for what a belief is and how we would go about updating it. How are we going to use it to pick actions? So basically what I mean is, given this belief, how does the policy use it to do something, to explore? So the strategy I'm going to talk about is posterior sampling, or Thompson sampling. And the idea is that you take a sample from the belief and then act as if that sample was the truth. So as an example of this, suppose that we sampled that we were in MDP 0 from our belief. We picked the first bin. So we should then take the action as if that was the MDP that we're in. And the optimal action in that case is to go left, right? Because then you hit the wall and you stay in the state, and you would accrue rewards if that was the MDP that you were in. Of course, in this case, it's not the MDP that you're in, right? So then you can update your belief, as we have there on the lower right, and you can repeat the procedure. You can sample again. Maybe this time you sample that you're in MDP 2, right? And then you would move right, because that would be the optimal strategy. So as you do this posterior sampling, you're smoothly trading off between exploration and exploitation, right? Because as you collect more experience, you're narrowing your belief distribution, so you get a better and better idea of, in this case, what task you're in. Okay, so we're going to use that intuition to build an algorithm. So just as we had before, what we want to do is maintain a posterior belief over the task and update it. So we're going to call that P of Z given C. So C here is going to denote context, but context or adaptation data, same thing. Okay, so, and we're going to make it a continuous distribution. So this is our continuous belief distribution, P of Z given C. And we're going to get it from our adaptation data, right? Then we'll sample from that distribution, and our agent will use samples from that belief in order to explore, just like we talked about with posterior sampling. So now kind of going back again to our little RL framework on the upper right-hand corner, now our function f, which used to be, for example, an RNN, used to be gradient descent, now it's a stochastic encoder, right? It's that phi thing that's going to take our data and produce our belief distribution. So before we get into how we're going to make all of this work practically, let's take a look at the results that we want to get. So this is posterior sampling in action for a real continuous control domain. So you're the agent, you start at that gray circle, and you know from meta training that your goal is somewhere on that unit circle, kind of denoted as an arc. But you don't know where on the unit circle your goal is. And you only get a reward when you're within the current goal. So in this example, you only get a reward when you're within that blue circle. So what we would hope is that if that belief represents our kind of task distribution, right, which we know is all along that arc, then when we sample from the belief, essentially what we're doing is we're sampling different goals along that arc. Right? And when we sample a goal, what do? We act optimally according to it. So we act as if, for example, the goal was way over there on the right-hand side. Of course, we soon find out that it's not because we get 0 reward. But this gives us kind of a easy way to eliminate hypotheses and narrow our estimate for where the goal would be. And this is actually data from the algorithm that we're going to build up. Okay, so how do we make this work in practice? Well, inferring the true posterior P of z given C is intractable, so we're going to use variational inference. So we'll approximate the posterior with Q of z given C, and we'll parameterize that distribution by phi. So that distribution will be the output of some nonlinear neural network. And similarly, we'll give an approximation for the prior, and so we can write down the elbow just like this. And this is the same elbow that you guys saw before when Chelsea derived variational inference, just probably with a bit of different notation. So the first term, right, is the likelihood term. And the second term we might call the regularization term or the information bottleneck. So let's think about semantically what this equation means, right? So we're trying to maximize this likelihood term subject to the regularization constraint, right? And the likelihood term is supposed to give us a belief over the task. So what supervision can we use for a belief over the task? So we have choices. We could, for example, reconstruct the reward and transition functions, right? If we did that, then we know that our representation has the information of what MDP it is because it's able to reconstruct the rewards and transitions. Another option we can use, which is the one we're going to choose here, is we could adopt the Bellman error. And so this will just be essentially training a Q function. And of course, Bellman error is not actually a likelihood, but if you squint a little and you read the control as inference tutorial, it might start to look like one. And so we're just going to wave our hands a bit and say that that's okay. Maybe a more intuitive way to think about it, though, rather than is the Bellman error a likelihood, is to think about it as information bottleneck. So in the information bottleneck point of view, you want to maximize that first term, that R term, right, subject to the Kale constraint. And what that means is you want to pass enough information through that Z such that you get good predictions for R, right, such that you get good Bellman error. But you don't want to pass any more information than that. And that's what the Kale term does, right? The Kale term tries to maximize the entropy, so it says less information. The Bellman error says more information. And so as you have these kind of two competing objectives, what you get is just the information you need for the Bellman error. Does that make sense? Any questions about this? Cool. Okay. So one more thing before we're ready to put the algorithm together is we didn't really talk about what the structure of that phi is, right? I just kind of waved my hands and said it was a neural network that takes in all of your experience and produces this distribution. Great. But let's look inside that a bit more and see how we want to design that element. So remember, our goal is to just infer a belief over the task. And to do that, because of the Markov property, we don't actually have to retain the order of the transitions that we saw them in, right? So it doesn't matter for all the transitions we've seen so far, it doesn't matter that we encode them in the order we saw them. Because of the Markov property, all we need is S, A, S prime R, right? And that defines the reward function and the transitions. So we can encode them in a totally permutation invariant way, which is exactly what we're going to do. And so what we're going to do is just take each tuple SAS prime R and encode it independently to produce a Gaussian factor, and then multiply those Gaussian factors together to get a Gaussian posterior. And we're just going to use Gaussians because they make the reparameterization trick nice. So why would we want to do this as opposed to using an RNN? Well, mostly for implementation reasons, because this approach is going to be faster to train, more stable to train, and generally kind of simple architectures are going to work better. You can also replace this with an RNN, and probably with a bit more tuning, it'll also work. Okay, so we're almost ready to construct the algorithm, but now we need to talk about off-policy RL so we can put that piece in. Okay, so here, we're going to build on the algorithm soft actor critic. And I'm not going to go too deeply into this, but I'll give some pointers for references if you're interested. So let's just kind of look at it from a high level. So the soft part, what does that mean? That means maximize rewards, right? So in this equation at the top, maximize expected returns, that's same from policy gradient. But then also maximize the entropy of the policy. And they do this in soft actor critic because it gives them like some better exploration properties when they're learning. Oops. Okay, and then the actor critic part, what does that mean? Well, we just model both the actor and the critic as kind of separate agents, right? And we're going to train the critic, which is the Q function here, with the Bellman error. And then we're going to train the actor to take actions that give us high Q values and also give us high entropy. And for the derivation of like how all of this kind of falls out, I would refer you to the control as inference tutorial by Sergey Levin, as well as the original SAC paper. Is this enough detail for going forward? Yeah.
I've also heard the term like is this the entropy bonus when people say that the policy is getting an entropy bonus? I mean, alpha H, I assume is shared.
Right. So it's here. It's not. Yeah. It's basically the same.
It is the same.
Mm-hmm.
Seems really similar to A3C. Is that another advantage actor critic?
Mm-hmm.
Briefly describe what the differences are.
I think that would take maybe more divergence, but basically, so SAC is derived from a framework where you model the whole thing as a probabilistic graphical model, and then you can basically relate the probability of your trajectory being optimal to the exponent of your rewards. And once you kind of make this assumption, then you can basically, like that assumption basically leads directly to this algorithm. And A2C doesn't start from that kind of framework. Okay, so just some results from this algorithm. It does pretty good on humanoid, and they ran it on this kind of cool claw robot at Berkeley, and it learns to turn the valve. And so this algorithm right now is the kind of highest performing and most sample efficient algorithm that we're using. And so we're really interested in being able to build on top of this algorithm for our meta-learning uses. Okay, so here's kind of a simplified soft actor critic in a diagram form. And so it's off policy. We're going to maintain a replay buffer as we collect data. And we're going to optimize both the actor and the critic with their respective losses. Okay, so now let's add our task belief distribution on top of this algorithm. So how's that going to work? So again, we're going to maintain this approximate belief posterior, the Q of Z given C, right? And we're going to take samples from it and pass those to the actor and critic. So now the actor and critic essentially are getting a state that's the concatenation of the original state of the MDP with the Z variable, right? And where Z here includes, is representing a task ID in some sense, right? And that KL term comes from the regularization from the variational inference, as we talked about before. And you'll notice that we backpropagate the critic loss into the encoder. And that's the Bellman error likelihood term that we saw before. Okay, so now let's just look at some results from this algorithm that we've put together. So I'm going to show results on these 4 domains. And so the agents we're going to be looking at are the cheetah, humanoid, ant, and walker. And we'll look at meta-training distributions that differ both in reward function and in dynamics. So for the first 3 agents, we're going to look at variable reward function. So that means which direction you move in, your target velocity, or goal position. And then for the final agent, we'll look at varying dynamics. So that will be like the masses and physical parameters of the agent. So here is the first algorithms that we looked at, evaluated on these tasks. So in that light greenish color, we have RL squared, which is an instantiation of the recurrent method that we talked about at the beginning. And then in purple and in yellow, we have kind of 2 variants of the gradient-based approach. And so this is just kind of for baseline, how well things do. And we're on a log scale here, which is why the curves kind of trend up like that way. Okay, and then in blue here is the algorithm that we just put together. So it's, as you can see, it's about 20 to 100 times more sample efficient and is also outperforming the previous approaches. And the reason it's able to do this is because it's leveraging that off-policy algorithm SAC that we just talked about in the meta-learning context. Okay, so why does this view that we took of meta-RL as a POMDP and wanting to have a belief over the task, why does that make off-policy RL easier? Like going back to that question where I was showing the distribution of the dogs and like it's better if you have a test task that's in distribution, how does this help us with that? So the interesting thing is that this approach allows us to separate the data that we use to infer the task, right at the top with phi, from the data that we use to train the RL agent. And so what this means is that we can address the distribution shift by making that adaptation data on policy, but making the rest of the data used to train the actor critic off policy. So, and this can still get us big sample efficiency speedups because if you think about it, probably a lot of the data that you're using is to figure out how to figure out policy behaviors that are like common across all of the tasks, right? So in the example of navigating to different positions, the knowledge of just how to walk at all is not task specific, right? And we can learn that off policy through kind of the bottom half of this figure. Whereas the top half, which goes through SC, can be on policy. And we have this kind of knob that we can turn to test, you know, how off policy can we make that data or not. Does that make sense? Yeah.
After I explore, I'm updating the inference parameters only for Z. Like, I mean in the test phase.
Right.
So you train, but then when I go and I see a new thing, the only parameters that are changing as I accumulate data from the new task is I guess Q feed.
So actually no parameters change at all. All of the parameters of the model are fixed. So it's like the RNN case in that regard, right? Where after meta-training is done, your parameters are fixed. So then what's changing here is the Z, the belief distribution, the Q of Z given C. So as you accumulate data, right, you are updating your estimate of the belief with the meta-trained phi parameters. Yeah.
Empirically, are you seeing the variance on that Z monotonically decreasing over the course of the task?
Yeah.
Okay, it does narrow down and stays constant throughout the rest of the task?
Yeah, I mean, kind of by construction, because of this multiplication, it tends to decrease. And then at some point, it just kind of stabilizes, yeah. Yeah.
I just saw that. Could you read the plot comparing the algorithms?
Yeah.
And I'm curious for your comments on, like, RL squared's doing pretty, so I'm curious why POMDP, which I'm not familiar with, is doing better on humanoid direction 2D, which is like probably one of the harder tasks.
Yeah. Yeah.
Whereas RL squared is doing so much better on just everything else. Could you comment on that?
So why RL, shoot, I used to know why RL squared or POMP was better on that one. There's like 2 versions of humanoid. Let me get back to you on that. But in general, the different algorithms, so POMP is basically MAML, but it's implemented on top of a different policy gradient algorithm. So MAML is built on top of TRPO, which is trust region policy optimization, and POMP is built on top of PPO. And there's some like little things you have to do to make that work. PPO in general is just a better performing algorithm, so in general POMP outperforms MAML. And then RL squared here also is implemented on top of PPO, which actually makes it improve a lot more over previous results, which were usually plotted with TRPO. So there's a lot of variables in RL, and you kind of have to get all of them right to really have a fair comparison. The other thing, while I'm thinking about that humanoid thing, the other thing I would say is that these curves are a bit misleading in terms of if you actually care about what the agents are doing, it's not really working in some of the cases. So for example, in that humanoid case, what you want is the humanoid to run forward or backward or in different directions, but none of these algorithms are actually achieving that reward. So this algorithm in blue is essentially just standing up for longer than other algorithms. So I think that kind of points to the difficulty of optimization in MedRL in general, because we know we can train a single task policy with SAC on humanoid, right? But when we go to the meta case, we're not able to achieve that same performance. So the curves can be a little misleading in some cases. That's the only one that's the only environment here where that's true. The other ones actually do the task to some degree. Okay, we talked about that. So I talk about some limitations of this method. So posterior sampling is pretty good, and there's a reference at the end for a paper that shows you can show a regret bound for posterior sampling. That's pretty good. But it's not optimal, obviously. And here, like this, the same diagram that I showed it off with also shows off why it's not optimal, right? Because if you're in this environment, the best thing to do is to go out to the arc and simply walk along the arc until you find the goal. And posterior sampling can't do this. And so the algorithm we built also can't do this. So it's, in some cases, it's going to have, potentially pretty bad exploration, or pretty far from optimal exploration. So one kind of interesting way to look at this, I think, is to look at the difference between that Mason algorithm that we saw in the first half and what we just designed here. So to get a bit into the details, the difference is in how you constrain that latent distribution, and if you constrain it before you do the adaptation or after. And so graphically, the difference is that in the algorithm we saw before, so let's let the yellow be the prior z distribution, right? You start off with samples from the prior, and then when you adapt, your distributions move away from that prior. And that's because you're constraining the pre-updated distribution to be close to the unit Gaussian, right? Not the post-updated one. So essentially, that kind of separates your exploration trajectories, which are like in the yellow region, from your task optimal trajectories, which are in the different blue regions, depending on the task. Versus the method we just described, what we just built up, the off-policy method, Pearl, what it's doing is it's constraining the post-adapted z distribution to the prior, right? Remember that KL regularization term. So essentially what that's doing is it's trying to get all of the task distributions to kind of overlap with each other and with the prior. And so essentially in the Pearl approach, you're not going to learn, you have no chance of learning optimal exploration trajectories, right? The latent distribution you learn is simply over the task distribution. And so all the exploration trajectories that you sample will just be optimal ones for some other task. Okay, so in summary, we first looked at how building on policy gradient RL, we can implement different meta-RL methods with recurrence or with optimization. We looked at how adaptation in meta-RL is both an exploration and an adaptation problem. And we looked at how we can improve exploration by conditioning the policy on latent variables. And in the second half, we looked at how meta-RL is a particular kind of POMDP and how using that kind of intuition, we can build up an algorithm that estimates a belief over the task and integrates well with off-policy RL. Any other questions? Yeah.
It seemed like this algorithm was a lot less stable in certain regions than the other algorithms. Do you know why that would be?
Here?
Yes.
I'm not sure if that's actually the case or if it's actually a problem with how we recorded it. I think it might be a problem with the frequency of how we recorded the data.
Oh, okay. On the log scale. Okay.
Yeah, it could be a bit more unstable. I mean, in general, off-policy algorithms tend to be more unstable than on-policy ones, though soft vector critic in the single task results is pretty stable. Yeah.
In the new MetaWorld paper, I spotted that, while PAL is still like super sample efficient, it's actually eventually outperformed by MAML and RL squared. I was wondering if you had any ideas for like why that is and how we could fix that.
In where?
So this is the MetaWorld paper, which was released by.
Oh yes, yeah, the MetaWorld paper. Yeah. Yeah. So that paper is just to give some context. That paper is interesting. They made, so this was people at Berkeley and Stanford, they made a data set of robot manipulation tasks in Mujoko that they have like 50 different tasks, and they're quite different tasks. So here we're looking at things like cheetah running at 10 meters per second versus 20 meters per second. But in this meta-world task distribution, they're actually looking at things, you know, like picking, pushing, moving, things that you would actually consider to be different tasks. And they evaluate these algorithms that we've looked at on this benchmark of tasks. And yeah, I actually haven't seen the results myself, I've just heard about it. So I would say that in general, so off-policy RL to begin with is less stable than on-policy. Partly for like the same distribution shift reason that we talked about earlier, right? Like you're expected to learn from data that's not from your current distribution, right? So that's one problem. And the second problem going against it is the meta-training optimization is itself hard. And that's hard even just in a multitask setting. So for example, forget about the adaptation stuff and just try to train a policy that can do 50 different tasks, given some indication of what task it's solving. That in itself is a difficult optimization problem because what ends up happening is the gradients from the different tasks can kind of interfere with each other and like kind of lock and prevent the model from learning anything. So I think those two problems combined are what's causing the issue, and I think looking at each of them in isolation will kind of yield progress that we can then put back together. Yeah.
So I kind of have two questions. The first is when you are like storing the experience, like the replay buffer, do you store as well like the optimal Z, like latent variables that you would find after doing the inner loop update step to the replay buffer? Or is that not part of the experience?
No, but sort of, in the sense that, so sort of yes, but through the data rather than through the Z's. So what I mean by that is when we collect data, we collect some of it with the policy conditioned on a z from the prior, and some of it with a z that's conditioned on, with a z that's computed from posterior trajectories. So essentially you get that effect, but it's through the data in the buffer.
So you're just storing the state action pairs in the data.
Mm-hmm.
Okay, and then the second question was, if you were to store the z, can you use that somehow as a way of like prioritizing the experience that you're sampling from the replay buffer to not have this distribution shift problem? Because you're only going to select like experience that's similar to the task that you're currently doing, based on the latency variable that you are using in posterior, or that you get computed with posterior part. So you can do like a sort of like, probabilistic sampling over the experience using Z.
Yeah, so doing some kind of like prioritization over the replay buffer.
Might that, I don't know, be one way of like to do some this stuff you got.
So, yeah, I'm not sure how addressing the distribution shift explicitly. I mean, I guess so. Okay, we're kind of doing that, right? When we sample the context from the replay buffer, so that SC thing is representing like a sampling operator, which essentially only samples the most recent things, so that the data is as on policy as possible. So that seems like kind of what you're getting at in terms of addressing the distribution shift. Yeah, in general, there's other techniques for like how you might better sample from the replay buffer that you could probably marry with this. Yeah.
So just to clarify, so at test time, you don't sample any of the experience from like training at all, right? It's basically just that same experience that you're collecting on policies, then going fed back to the feed to update your legal requirements.
Right, because remember at test time, it's a brand new task. Yeah, so one, well, okay, that's another thing, but yes, yeah, sorry.
So during meta training, you're training both your encoder and your SAC, like your actor critic, right?
Mm-hmm.
So the actor critic, when it comes to like the latent variable, is kind of tracking the moving target, right? Because your embedding is changing during meta training.
Yep.
Do you use like target networks or like anything to mitigate that, or does everything just kind of work well?
Yeah, so SAC uses a target network already, and we also use that. Yeah, it is a bit of a moving target. One thing you could consider doing is if you were not using the Bellman error to train the encoder, if you were using like reconstructing the rewards and the transitions, then you could train that offline beforehand, right, and then do this. And I haven't experimented with that in particular. I've experimented with training it all in parallel, but with the reward reconstruction objective instead of the Bellman error, and it does a bit worse. Yeah.
Sorry. So also at meta test time, you're sampling your context parameter at the beginning of the episode, and then running it for a whole episode,
Mm-hmm.
and then reconditioning your context distribution on like the trajectory that you just did. Could you imagine like if you at every step in your episode resampled your context parameter, you lose your like coherence of like what policy you're following, but maybe you have some more like adaptation or like better exploration. I don't know if you tried that.
Yeah, I think especially, so that does work in task distributions where exploration is not as important. So for example, in the Mujoko benchmarks where you get dense rewards at every time step, that actually works fine. But it doesn't work, for example, in the sparse, this case. But in general, I think getting an off-policy method that can learn, that has that property of being able to learn optimal exploration trajectories is kind of an open question. I haven't got anything to work there yet.
For that, actually, we do want to carry over some state across all of the different tasks, like a hidden state across all the tasks, kind of like an RL squared?
So in RL squared, you don't carry the hidden state across the task. Only the episode, right? Because the hidden state in RL squared is supposed to tell you what task you're in, essentially, or it's supposed to give you some task-specific information. So one interesting idea, which we tried and didn't work, is sort of getting at this idea of like, can we use different data from different tasks can I take data from task A and like use it for task B? Like, why can't I do that? That's annoying. So if you wanted to do that, what you'd have to do is like relabel the data, right? So because you say the reward function changes between task A and task B. If I could relabel task A data with the task B reward function, I could use it, and that'd be great, right? So what we tried to do is essentially put a model for the rewards that's trained from Z. So basically have Z reconstruct the rewards. And so we essentially have a generative model of rewards, and we train this across all the meta-training tasks. So now it should be that given a Z, I get some reward function. And then I could use that reward function to relabel some data. It didn't work. But I think figuring out how to reuse data from tasks for each other would be really useful in terms of making this more sample efficient.
In Hero, the hierarchical RL paper, they do a similar thing with like goal condition relabeling of the
Yep.
rewards, right?
Yep.
So in that case, like why does that work? Is it because they're not trying to do a generative model of Z's in that case?
Yeah, probably. Yeah, I mean, if you're in a sparse reward case, then you're like any kind of signal is going to help you a lot, versus if you're in this case where you have some labeled data and you just want to kind of generate more to help you, like it's less clear if it'll help you, I guess. Cool. I heard this ends at 2:50, so thanks all for coming.